Okay, hi all, good soul, and my name is Parvathi Kurup, and I'll be taking today's presentation on the Engineering Center at Habitat Marte. So, coming to the content that I'll be covering in this presentation. So, I'll start off with the external and internal design. um, uh, just a small proposal of the structural design of the modules that I came across and I found interesting. And then I would be talking about the resources necessary for operations at the center, such as the machines and technology with the equipment used for various operations, and also the possible resources to generate in situ, and also the resources that could be transported from Earth. Then I'll be doing an overview of the organizational structure, the positions, the guidelines that is to be followed by the other facilities, also on the astronaut training program, and I've also linked in a couple of videos. I'll also be talking about the protocols that would be followed at the facility that we have to follow. These include facility or specific protocols, protocols of safety, protocol for occupancy, entertainment, or leisure activities, protocols for 3D printing, and then I'll be talking about the spin-offs, the major takeaway that us as Earthlings can get from these missions, and a few technology and outputs that could be applied to Earth, and finally the impacts that uh, that basically act upon sustainable development goals. So coming to the external and internal design. So this is the kind of structure that I came across and I found really interesting. And I actually came across two different uh, conceptual designs for the entire engineering center. And I thought of kind of combining the two. So the first one, what I came across was the Marsha conceptual design by the AI Space Factory. And the second conceptual idea I came across was it's known as the Cal Rowley CPP lab, and it was created by a team of civil engineering and architecture students from the California State Polytechnic University. So the talking about the external design of the Marsha habitat. So it's basically a 3D printed structure that's mainly made up of a thermoplastic, a basalt fiber reinforced PLA, and it employs a dual shell scheme. So it's basically to isolate the hazardous environment, um, which is uh, which is not fit for human habitation. So it's going to protect us, and it also reduces the structural stresses which are brought on by the extreme fluctuation in Mars temperature. So this dual structure, it really helps to kind of keep the interior environment of the body safe, and also it's effective. And we'll see how that is in the next slide. So this is a just a rough sketch of the idea I had of kind of combining the two conceptual ideas of um, the Marsha modules. So I was thinking of designing two modules connected by the Cal Rowley module in between them. So it acts as a walkway or a corridor connecting the two modules. And as you can see, there's also an EVA docking module or like a airlock unit that is attached to the first module. So as you can see in the in the sketch, in the sketch, you can see that there's module one and module two, and each module has minor differences um, between the amenities that are available in each of their floors. So the idea of Calgary is basically in the previous slide you could see that it's closed. It's a closed structure and it's easier for transportation, but it can be opened and it can be used as a full-fledged module. But in this case, I'm just adapting it as a corridor or a walkway. So these are just the internal design, the floor plans. Uh, it's not exactly what's shown here. I've just modified, like what I have in mind is a modification of what's shown here. So the ground floor, what I was thinking of was the EVA docking and the airlock unit, then the workshop and manufacturing unit, and the maintenance unit, and the first aid room. And coming to the second floor, we have the kitchen, the recreation room or the lounge, the sleeping pods or the bunk beds, and washroom facilities. On the third floor, we have an astronomical observatory, which I thought would be really crucial if you want to carry out astronomical observations or research. Um, Coming to module two, so this is where the control room unit for the entire engineering center facility will be. This also has the wet lab and the dry lab, the two research labs. It has a first aid room again. The second floor has a kitchen, again, same as module one, a lounge or recreation room and sleeping pods or bunk beds. And third floor has a greenhouse for growing a few plants. Now, coming to the resources which are necessary for operations at the center, um, I'll be talking about the machines and technologies that are quite crucial for the center and the mission. So starting with additive manufacturing, which is again 3D printing, there are multiple applications here, and what I would like to really see in future missions or um, what I really found interesting was the development of metal printing capabilities in space. And right now, NASA is working to develop the metal printing capabilities for the International Space Station and as well as future space missions. On the Earth, meanwhile, the preferred 3D printing, metal 3D printing method is selective laser melting. So my proposal was to kind of inculcate a similar technology on our Mars habitat, which would be quite useful to build different structures and carry out different engineering projects and such. So, and another type of 3D printing technology that could be used is using materials like composites that could be incorporated in large 3D printers that can be used to build modules or habitat buildings on Mars. Next, yeah, so this is just a continuation of the additive manufacturing unit. Another interesting concept or technology, sorry, not concept, technology that I came across is the hybrid 3D printing, which is currently being used in the International Space Station. It's known as the in-space refabricator. And this 3D printer, it can recycle the hard polymer plastic and like n number of times to make new items. And I think that's one of the perks of this hybrid 3D printing technology. Then coming to the workshop or the manufacturing space. So the workshop requires multiple tools to function on a daily basis. And the tools are like varying from hand tools to machining tools. Um, then we have gas supply units for welding. And as you can see, I've mentioned a couple of tools that could be quite useful, such as drilling machine, wrenches, filing tools, screwdrivers. All these would really be quite handy to have at the engineering center. And especially since we have a maintenance unit attached to our center as well. So yeah, coming to the next slide. Yeah, this is again just a continuation of what I had imagined the space would look like, the manufacturing space would look like. So I would like to imagine it as a maker space where you can pretty much build what you like with the available resources that you have. And for that, to enable that, you need like a lot of tools again, which again I have mentioned a few CNC machines. And if you would like to build something which is electronic in nature, then there should be a supply of circuit boards, connecting wires, electronic components, batteries, soldering equipment, and so on. And other miscellaneous tools also, like adhesives and just to carry out your engineering projects, basically. Coming to the wet lab and dry lab. So just to differentiate, wet labs are basically for carrying out research and analyzing matter which is in liquid form, biological matter or chemicals, whereas dry labs are focused on computational research, physics and engineering research. So each has its own respective set of tools and equipments, and well, I could have listed it out all, but I just picked a few which seemed important just to mention. So a wet lab would require equipment such as your petri dishes, chemicals, test tubes, microscope, and so on. Whereas dry lab is one that primarily uses electronic equipment, so like your robotics lab. Now, coming to the other technologies that would be necessary to the operation of the center, uh, we really need um, a technology where we can explore the Martian surface like never before, and that's where rovers, drones, and EV vehicles help us. So as we know, rovers has been used extensively for several Mars missions by NASA, and rovers can basically go to sites where maybe it's not possible for humans to go, and it can collect data, it can collect soil samples, it can collect rock samples which can be stored and later studied and analyzed at our lab facility. And similarly, we also need drone technology on our Mars habitat, um, because it's really useful as drones have a good range when range of flight, I mean. So you can really observe multiple sites in a day, and really collect all that data of the surface of Mars that you have observed, and you can use that again to study the Martian surface. Coming to EVA vehicles, so this has not yet been implemented, of course, um, where you get to drive on the Martian surface in a vehicle during an extravehicular activity. So but this is really useful when it comes to doing research in faraway sites, that is, locations that are quite at a distance from our habitat. So yeah, I feel EVA vehicles are like quite important in that manner. Another important an integral part of the engineering center is the integrated control systems. These systems just take care of all your life needs basically, and it's kind of it basically secures um, the crew members who are living on the habitat. And I've mentioned a few of the integrated control systems that are crucial. There's the crew healthcare system, the environmental control and life support system, computers and data management systems. And then we require systems that could possibly um, help with the propulsion, the guidance, navigation, and control, since we are using um, the rovers, and we're using technology like the drones. We require a sort of a guidance, navigation, and control system. We also require a communication system, and then a thermal control system to control the interior temperatures, and we require an electric power system. So these are also I would be mentioning about the power supply to the engineering center separately in the coming slides. So that's hence I that's the reason I mentioned the electrical power system here, because I felt it was needed that the engineering center requires a separate power supply apart from the power supply from the main power station. So, as I was saying, these systems are crucial to provide a safe, livable, and comfortable environment in which the crew members can perform your daily activities or scientific research or projects. So as I mentioned before, coming to the power supply, um, a separate power source is needed to run the engineering center in full capacity, because um, the I as I mentioned, the technology and the equipments required, um, I imagine that it would consume a lot of power, and because of that, it would require at least multiple power sources to kind of back it up. So one way you can do that, or multiple, there are actually multiple ways you can do that. Those are through nuclear reactors, or solar arrays, or wind turbines, um, and the I so it, I feel that a combination of these power sources would kind of help in functioning of the engineering center. Coming to the in situ resource utilization, so in situ resource utilization is the practice of collection, processing, storing, and usage of the materials that are found on extraterrestrial objects or astronomical objects, that could replace materials that would otherwise have to be brought all the way from Earth. So the this is an important aspect, I believe, because it helps us save um, a lot of cost, a lot of time, energy with respect to transporting resources, or the supply of resources. Um, so a few known resources or materials that can be obtained from the Martian surface are it is your Martian soil. Then there's the soil, Martian concrete, which is a derived material that you can get from mixing Martian soil with the salt, or like another composite. and you can use that to build your habitat or to expand it further. And we have water, as we've seen from the ice deposits, and there's carbon dioxide, which is another um, available source of gas, and the Martian atmosphere contains 95, around 95 to 96 percentage of carbon dioxide. So now coming to the engineering center management. So this is the organizational structure, what I had in mind. So it starts off with the facility chief, who is the head of the engineering center, and um, the other members fall into either a researcher, engineer, a lab assistant, or a technician. And just a brief about what their duties look like. So the facility chief, of course, overlooks all the activities at the engineering center, checks up with the maintenance of the facility, also updates the main station on the activities and requirements of the engineering center. And facility chief is also trained in EVA activities, so they can go out and conduct EVA experiments or research. Coming to a researcher carries out experiments in in mostly science fields. I would say I don't, but I don't want to restrict it only to science fields, but mostly science fields such as astrobiology, astronomy, geology, and so on. And a researcher should be knowledgeable in the above mentioned fields of expertise, of course, um, experienced in handling lab equipments and instruments, and also trained in EV activities, and a researcher reports to the facility chief while working at the center. Similarly, an engineer carries out the design and manufacturing activities of the projects at the manufacturing unit, um, and an engineer should be knowledgeable in multiple, there are actually multiple fields from where an engineer could come, just like a researcher. So I have mentioned a few like seemingly common fields that could be quite. Hello, sorry. Yeah, so as I was saying, there are multiple fields. I've mentioned a few: aerospace engineering, computer sciences, electronics, and so on. An engineer could be experienced in handling devices, machinery, the workshop tools, especially. And the engineer is also trained in EV activities and reports to the facility chief. The lab assistants are responsible for helping technologists and scientists during the lab tests and research. Um, these professionals, they have to have in-depth knowledge of the basic laboratory techniques or equipment at least. Their duties also include processing samples, classifying results, and recording findings. And I have mentioned that they are trained in EV activities as well. So just to clarify, I believe that I'm assuming that all the members are trained and trained to perform the activities. So yeah, and a lab assistant reports to the facility chief. Technician tasks include looking after the technical equipment, doing maintenance work or practical work in a lab or the workshop. So I have mentioned in a lab here, so I mean the dry lab where there could be research related to robotics and such happening. And a technician must be capable enough to handle the tools, the machinery, computer system, and also must be able to fix all these systems in case any problem arises. And of course, the technician is also, as mentioned in the other cases, trained in the UV activities and reports to the facility chief. So coming to the resources needed for a week, um, I have just briefly touched upon the power requirements, food and water requirements, and supply of weekly lab or workshop exhaustibles, and weekly supply for personal care items and first aid kit. So food requirement for astronaut, I'm assuming it's around 1 kg per day, and water requirement is around 2 to 3 liters per day. Power requirements are 15 to 25 megawatts of power per day, and this could come across as quite a high number of power, but I've actually compared the uh, the values of what the power supply should be like on a space habitat versus the power supply per day at an actual engineering facility or a factory or some sort of workshop. So um, I kind of came down to this value of between 15 and 25. And supply of weekly lab or workshop exhaustibles, it really depends on the number of experiments being carried out per week. So I really could not come up with a certain number for these exhaustibles, for the amount of exhaustibles required per week, because it really depends on the nature of the experiment also. And and the engineering center especially, it has not just a single lab or a single facility, it has multiple labs and multiple workshop spaces and whatnot. So I just felt that the number was a little ambiguous, or it would be a little ambiguous. Then weekly supply for your personal care items, your first aid kit, and your toiletries or any medicines and such. And I've given the tentative value as 8 because there's 8 members, and I'm assuming each member would get a kit. Um, so now coming to the guidelines that is to be provided to the other facilities. Um, Most importantly, sticking to the general protocols and safety measures is first and foremost very important. And the activities from the center and docking mechanism have separate protocols, so they're not in junction with the engineering center protocols. So there would be, I'm imagining there would be a separate manual for it. Um, then crew members have to take turns and sometimes share tools and even the space that they have to work in, because some days there would be uh, a scenario where 2 people have to use the wet lab to carry out experiments, or 2 people have to use the dry lab or the workshop area. So really the sharing of the tools in the space is what uh, we have to work towards. And each experiment and workshop time, um, it has to be decided or scheduled 1 week in advance. Practicing cleanliness and discipline in the center is really important. Then crew members also have the option to take rest in between experiments, as there are sleeping pods available in module 1 and module 2. And there's also room for leisure activities and a small kitchen. So if you feel hungry while in the middle of working, or if you're on a break, you can always get some food. And this is available on the third floor of the module, of the first module. And an elevator can be taken to access the higher floors. Coming to the astronaut training program. So these are just again a brief of the duties that I have mentioned. The engineer should be knowledgeable and have experience in robotics, or at least electronics or computer sciences, and mechanical engineers should be well equipped to handle the machinery, hand tools, devices used in the workshop floor. Technicians, again, as mentioned before, should be able to handle and fix problems. And as a part of the training, the each of these um, role role members should ensure that they have knowledge, they are knowledgeable in all these areas. Um, and researchers, again, must be quite adept at handling instruments, the chemicals, biomatter equipment, tools, and be able to identify problems and help the researchers when needed. These are a few videos that I came across. I apologize, I couldn't find much more than just 4 videos at the moment. Now, coming to the engineering center protocols. So these are the specific protocols of the facility. That is always wear protective clothing before operating high-risk machines or equipment or wherever necessary. EVA protocols, again, as mentioned before, given in separate instruction manual. Crew members can schedule their work time 1 week prior. Handling of every equipment and tool should be done with utmost care. And always making a record of the stages of the activities or experiments carried out in the workshop area or the labs is a must. And all crew members should ensure that they are maintaining cleanliness in the engineering center at all times. So they should ensure that they clean up after they're done using the space. And the crew members should also stick to the safety protocols. They should follow the instructions given in the manual, and they should follow the manual to the T before proceeding with the experiment or the workshop job or trying to operate any machine. And they can seek help. They can always seek help with the technician or the lab assistant if they're facing any issues. The machinery, devices, and the equipments that consume a lot of power unnecessarily and that are not being used must be switched off after each use unless a longer runtime is required. So there would be cases where you might have to 3D print something for a couple of hours. So at those in those scenarios, it's okay to leave the machinery turned on, but otherwise it's advisable to switch off so that we can save power, um, and also return the tools and instruments back to its place of storage after you're done with its usage, and maintain decorum and do not cause excessive disturbance to the other crew members. So these are the protocols for safety. That's the kind of a repetition of the general rules of the center, and it's mainly nothing but sticking to the rules, um, especially while operating a machine tool or an equipment. And you have to wear protective clothing, gloves, or goggles for appropriate workshop lab operations. So that's the first thing that you have to do before starting your job or your work at the lab or the manufacturing space. And you should always be alert while using the workshop or lab facilities. In case of emergencies like an outbreak of a fire, you should ensure you should follow the procedures that you had learned during your training before you try to help somebody else. And you should immediately wear a gas mask in the case of a fire hazard, a smoke, or a toxic gas leakage. Gas leakage. Refer to the manuals for instructions and all the precautionary measures. And it's important to memorize the emergency exits and procedures. And finally, seek medical help immediately if you're injured. The protocols for your leisure time or entertainment. So I have just listed a few leisure activities such as reading at the library, workouts at the gym, uh, board games or puzzles, yoga. You can also do a lot of photography. A lot of astronauts enjoy their photography time, and that's how you see all these beautiful pictures uh, from here on Earth. You can talk to your family, um, because and I think that's quite a rare and nice moment to have, because you may not be in touch with them for like months or so. And you can also celebrate festivals or special occasions with the crew members. Now, coming to the protocols for 3D printing. So, um, first and foremost, you need to identify the raw material that you're using. Since there are multiple 3D printing methods, so it's important to really know and decide upon what raw material you require. Pre-printing design and measurement. So before you're printing, it's important for you to really review the CAD model that has to be um, input to the machine. So you have to ensure that the design is optimized to be compatible with all the tolerances, because in 3D printing, what happens is that you may not be able to machine the internal cavities. You might be able to machine the external features, like you might be able to kind of achieve a better finishing. But the internal cavities, it's really difficult to be machined. So you have to ensure that you're inputting the file with the right tolerances and the right measurements and such. And also designs with acute angles, they're also known as overhangs. They might be needing additional supports. Um, Otherwise, your 3D printed model may not come out as you expected. Also do a post-printing check. Once a part comes out of the printer, the dimension should be measured prior to the original printing. Coming to, yeah, so this is just a continuation of the protocols. So again, design and measurement for post machining. So this is after printing and after your machining is done to remove any excess material from your model. So as mentioned before, it's always better if your initial design was optimized from the beginning to match with the machine, um, so that you can try to reduce secondary processes as maximum as possible. And then comes the final measurement and testing, where you can test the material properties, you can analyze the model, do the remaining procedures. So also an important point is the maintenance of the 3D printer and the entire 3D printing facility space. You need to clean it and maintain the 3D printer cleanliness and keep it fit. Coming to the spin-offs, so just a few points that tell us about the major takeaway that we can, as us as Earthlings, can get from these such missions, and especially the Mars mission. So there's the introduction of new methodologies with respect to carrying out operations in industries or labs, sustainable manufacturing practices such as your lean manufacturing methods, sustainable additive manufacturing, reuse or recycling of waste or byproducts within the manufacturing system, improved AI and computer systems, a better understanding of human physiology in harsh environments and how we can cope up with that. Then learning how plants, microorganisms, or any other living organisms grow and function or live in a low gravity or high radiation and low oxygen level environment. Better overall health, hygiene, and discipline practices. So Mars exploration can also help scientists learn about tremendous like shifts in the climate that could fundamentally alter planets. It could also help scientists to get a better understanding of how life might have occurred on certain planets and what are the conditions that could have led to the same. Um, then, so these are just like a kind of a continuation where I have specified certain technologies um, that that has really benefited mankind or would be benefiting as well in the future. So the first one is the drones and rovers. As mentioned before, we have better sensors and better range and better capabilities. Then we have highly advanced robotic arms that could perform delicate surgeries. And we have sustainable additive manufacturing capabilities for large structures or entire settlements, like our habitat on Mars. And we can also adapt the air and water purification systems developed for space usage that provides us with clean and fresh water, especially in the case when you're trekking or you're traveling and you require fresh water. And um, there's a lot of time where you may not be able to uh, get fresh water easily. It may not be available easily. So space exploration has really contributed in that front, in that development of water purification system. And modern firefighting equipment that uses lightweight firefighting materials, space exploration that depend on excellent digital imaging, image processing technology, which has been used on CAT scanners and radiography and etc. Then there's drug development using protein crystals and identifying unknown microbes in space. And a few applications of solar energy and wind energy techniques. The impacts on sustainable development goals. So I believe that these six sustainable development goals are majorly being impacted due to the operation of our infrastructure. So number one is affordable and clean energy. Thanks to the alternative sources of energy that we are incorporating. And of course, we have industry, innovation, and infrastructure. We are definitely contributing to that as we are coming up with new technology, new ways to kind of survive on a completely different environment. And we're building sustainable cities and communities as well. Um, or in the future, we would hopefully build sustainable communities on a different planet. And we are also conscious about our consumption. So there's responsible consumption of resources where we are trying to consume less and trying to reuse and recycle as much as possible. So space exploration really enables this. And we have we're also contributing to climate action, where again it's pretty much interrelated, where we're using clean energy, and hence that the same technology can be applied here on our planet and help take better strides in fighting climate change. And of course, there's partnership goals that are happening due to space exploration, where multiple countries come together to finally solve common problems or common goals. So I think that's really great to see that partnership. These are just a few references. And this is my contact info, my social media. Thank you. If you have any questions.